minimize reduce the number of dangling bond of the surface, because the reason why the surface go for this is because of minimization of energy. So you actually, this is a low energy state if you don't reconstruct your surface. And what happened? Well, what happened is that this atom has one dangling bond sticking out of the plane. Okay, what will happen is that reduce a 49 dangling bond system into just 29 dangling bond. And I let you read this to figure out how it can go there from one system to another. You should read about it, because that's a very interesting thing, how you can reduce the dangling bond. So the location of the atom is important. Why? Because that's where surface chemistry occurs, because that's where the absorption will occur. Because they have free electron dangling bonds sticking out of the surface, right? Out of this site, all these bright spots are the reactive sites. So the absorbing, if you put glycine on these, like my students do, then they would go for this site. Okay, they would go for this site. And the two halves are different. They have different surface chemistry. The folded half is more reactive than the unfolded half. Okay, so that you will find more absorption on the folded half compared to the unfolded half. Okay, so there are a lot of things you can do surface-specific chemistry with an STM microscope like this. Okay, so there are other things. I'm trying to move along here. So this is other people can take image too. So they have other microscopes. So there are different things that you can do. Step services. So when STM come along, they actually image another plane, which is a Silicon 100 service. This is the important one, right? The one that everybody used to build silicon chip, your Pentium, your PC processor is using Silicon 100 services. And what you found is that you see all these atomically sharp steps like this, right? And often you see that on semiconductor service. We can see this too, also on 111. You can do fancy thing, right? This is a surface of graphite, right? Graphite material at low temperature, 3.1 K. This is gold surfaces on room temperature and so forth. And you can get a library of stuff on this website. So there are Mandan, San Jose, IBM San Jose site has a nice video of how they build the IBM logo with STM, and then there are other sites that describe different things, different surface chemistry with using STM. So I like you to take a look at some of these images. They're absolutely fascinating, I think, because before STM come along, you really cannot see this atomic resolve, so-called atomic resolve system. So I have added a question to your assignment number 2. So you should take a look at it. It's on the, I think it's on your printout, so you don't need to write this down. So I want you to describe a sister technique which is called atomic force microscope. So after the invention of STM, these two guys continue to build on this. They of course they recognize the limitation of what STM can do. So these guys then come up with the idea, well, maybe we don't need to measure the tunneling current. Maybe we can do, if it's positioned close enough, maybe the two atoms may sense the force of each other, right? So there are repulsion force, of course. If you put one electron charge cloud to the next, to close enough, they will repel each other. So they consequently invented something called atomic force microscope, AFM. So a lot of you may have AFM, maybe heard about AFM, and may one day use it. And the working principle is a little bit different. Okay, the basic, this part, the microscope part, the tip part is still the same. Okay, the detection bit is a little bit different. Instead of detecting current, because they don't care about current anymore, care about the force between this atom and this atom, right? So what's the beauty of AFM? The beauty of AFM is that nowadays you don't need anything that can have electron, right? What does that mean? You don't need a conducting sample anymore, right? Conducting sample will have free electrons that let you go out. But so that's why in STM the other limitation is that you cannot measure insulating material, dielectric and stuff like that, because they have no electron to leak out, even if you apply potential. This thing, on the other hand, if you sense this force, even if you have non-conducting material, they will have a force. They will have the electrostatic force between these tip atom and surface atom, right? So now, all of a sudden with AFM, if you can somehow measure this force, the repulsion force between these two, you have a way to measure almost anything, right? You can measure protein, right, which is one of the very popular things to do. You can measure dielectric material and so forth. Okay. Now, the limitation, often quoted limitation, I think, is that in AFM, some people complain, okay, it's not as atomically resolved as the STM, and that's not because of the physics. It's because most people who are using AFM, they use it in air. They operate AFM in air. This is usually done in ultra vacuum. Why? Because you're doing it you're measuring tiny current, although you could do it in air as well. This is normally done in air, which does not require ultra vacuum. And because of that, you cannot really use a very atomically sharp tip to create this fine detail between the forces of this. If you can create an atomically sharp tip, then you would have the same resolution as STM. Okay? So typically then, this tip is of the order of 10 nanometer curvature, something like that. Whereas in STM, you would have an atomically sharp tip, and then you can see this. Okay? So I'd like you to find out, so I don't want to go into AFM, which is an important tool. I want you to do a little bit of work, homework, to figure out, to go read something and find out how AFM works, because it's related to STM. Find out the difference. And this is an exercise in question number 5 in assignment 2. It's an attempt to move you in that direction, to let you learn it yourself. Okay? So next, I'd like to tell you just a little bit about, get started at least, on the electronic structure of the surfaces. So we have finished the second module, if you like. We're moving on to the third module about the electronic structure of surfaces. And there are, in the interest of time, I want to cover about 8 topics like this. Okay, so before we can talk about this, we need to review some of the basics.